AP Chemistry, and welcome to IMFs. So first of all, let's make sure we are using the I part of that appropriately, okay? What we previously talked about, what we spent the last entire chapter basically introducing, right, is the concept of intramolecular forces, okay? The attraction that happens within, right, because intra means within, so the attractions that happen within a given substance, right? So it is like the covalent bond that holds these together, right? What was I going to say? I don't know. But the covalent bond that holds these together, right? These are always going to be stronger than our intermolecular forces, right? Where inter, right, is between, right? So these are always going to be the forces between molecules, okay? All the same ideas apply, right? Where we often use Coulomb's law, right? The force of attraction is equal to my charges relative to my distance, right? Wherein, when we're talking about intermolecular forces, right, we're not talking about fully charged species, but we can have partial positives, right, and partial negatives, and we can still talk about distance between my particles, right? Now, if we talk just a tiny bit about distance here, right, by default, your intermolecular forces aren't going to be as strong because, by default, they're going to be further apart, right? When we think about a covalent bond, right, we're talking on the order of angstroms, right? 10 to the negative 10 meters or closer, right? That's how far away my atoms are from one another. Here we're talking about the distance between our molecules, which by default is a little bit greater, okay? Anyway, this is just a introduction. Make sure inter and intra, keep them straight. Okay, next up. First type, LDFs, London dispersion forces, present in every single thing that has electrons, okay? Like your book talks about, on average, the electrons are evenly distributed within a given atom, right? Instantaneously, though, right? So when we talk about what an LDF is, it is an instantaneous dipole, right? Meaning that at any given point in time, at any given instant, the electrons in an atom may be unevenly distributed throughout the atom. At any given instant, the electrons in an atom may be unevenly distributed within the atom, okay? And if, for example, at this instant in time, right, the electrons are more on one side, which means that at that instant we get a polarization, an instant dipole. And then that one induces a dipole on its neighbor, this one induces a dipole on its neighbor, and we get a series of induced dipoles. Right? So the way that we describe an LDF is that an instantaneous dipole in one atom then induces a dipole in its neighbor, right? And then we get this network of instantaneous and induced attractions within an entire species, okay? So again, this has to do with electrons, which means that the more electrons you have, the greater your polarizability, okay? Any discussion of London dispersion forces and their relative strengths needs to boil down to polarizability. If you're missing that word in your discussion, I'm probably not going to give you credit, okay? And so when we say that something has more electrons, it is more polarizable, right? More able to be polar at any given instant in time, okay? Your book talks about how it does correlate to molar mass, which it does, but that's not the molar mass in and of itself, right? It's not that there's more protons and that's why it's more likely to have a stronger LDF. It's not because there are more neutrons, it's because there are more electrons. So a good answer is going to say more electrons, more polarizable, right? And then we can say, in terms of what it is, instantaneous dipole, induced dipole on its neighbor, a network of these attractions spread throughout an entire sample. Okay, so this is LDFs, right? LDF strengths, right? So if we look here, right, obviously if we're just looking at our noble gases, right, as we go down the group of noble gases, we'll see that, yes, our boiling point increases as our molar mass increases, because as the molar mass increases, our sample has more electrons and is more polarizable, therefore more likely to have an instantaneous dipole and induced dipoles on its neighbors, leading to a network of instantaneous attractions throughout the given sample, okay? And likewise, the same thing with our halogens, right? Which, going back to things that we've talked about previously, right? So back when we talked about 5 and 19, we said you needed to memorize that these two are gases at room temperature. This is a liquid, and this is a solid at room temperature, right? And this is the explanation for why, right? Iodine's London dispersion forces are strong enough, right, that is a solid at room temperature. Bromines is in between and it's a liquid, and these two are gases. Okay. Oh yes, and in terms of these are a simple LDF discussion because, right, noble gases have no other attractive force, right, and nonpolar species, and we know that these are all nonpolar because, right, it is the same thing stuck to the same thing, same electronegativity, therefore there's no unequal sharing. All of these are nonpolar, which is why we're only talking about London dispersion. Okay, then that brings us to dipole-dipole forces, which really are the easiest ones to discuss. In order to have a dipole force, you must be a polar molecule, right? So again, we need to know our VSEPR table really, really well. Again, really, really well. So when we see a molecule, we can quickly deduce, polar or nonpolar, so we can continue on with our discussion, right? If you have to waste a million years, or a long time, right, drawing out a Lewis structure, and then you get the Lewis structure wrong, and then you get the VSEPR wrong, right? This is stuff that needs to be second nature. Okay. Anyway, when we talk about dipole-dipole forces, this is what we should think of when we think of like bar magnets, right? How opposite ends of a magnet are attracted to one another. Same thing in a dipole-dipole force, right? Here we have the negative end of my molecule is blue. The positive end of my molecule would be this other white end, right? And so if we look, right, the opposite ends are attracted to one another. All right, ranking dipole forces, right? So with the London dispersion forces, it was as simple as who has more electrons, right? Dipole forces are a little bit more thoughtful in that the structure really does matter. Okay, so this figure from your book is just sort of one, if we equalize molar mass, which means we equalize the number of electrons on average, right? And we look here, what kind of models are these called again? Right, these are known as space-filling models, and they do a very good job of showing polarity, right? In that here, when we have this dimethyl ether and the oxygen is stuck in the middle, right? So it'd be like COC, where my oxygen is actually part of the backbone, right? Here are my H's. So when my O is a part of the backbone, yes, that molecule is a little bit polar. Note 1.3 debis, okay? Acetaldehyde, right? If we look here, is 2.7 debis and is a little bit more polar, right? Because we have the oxygen that's actually sticking out now, right? Oxygen, CH3, okay? And then when we look over here, acetonitrile, right? We actually have this over here all by itself, right? And this is a very electronegative species, right? And so we understand that this is far more polar, right? Because one, we have a more electronegative species, right? And it is more separated from the rest of the molecule. Okay. Beyond dipole-dipole and London dispersion forces, so London dispersion forces present in anything with electrons, right? Dipole-dipole forces present in all polar species. But it turns out that when we look at this chart here, right, which shows a lot of information actually, we'll see here, right, that on average as we go down, for example, as we go down group 4, as we go down group 7, go down group 5, and go down group 6, right, we'll see that on average, the boiling point increases. Okay, so in terms of increasing, so here we just have an increasing. So here, right, for these, since this one is nonpolar, right, we understand that, well, tetrahedral, nonpolar, we understand that all of these are nonpolar. So we understand that this increase in boiling point is strictly due to, right, an increase in polarizability due to an increased number of total electrons. Therefore, we get an increase in boiling point. Now, based on what we know about what NH3 looks like, what does NH3 look like? Right, it is trigonal pyramid polar, right? So if we look here, and we look at this, right? Are we increasing polarity as we go down the group? No, that's right. As we go down the group, our molecule becomes less polar, right? In that if we think about our periodic table, nitrogen is going to be the most electronegative, and the electronegativity is going to decrease as we go down the group, okay? Which means that the polarity of the molecule is less as we go down the group. But this is a testament to what an increase in the number of electrons can do, right? So when we get things with like boatloads of electrons, right, in my entire molecule, for example, then yeah, those have really, really strong IMFs when we get a large sum of them, right? And this is what that is sort of evidence to, right? We do get a steady increase in boiling point as we have more electrons, so it's more polarizable, okay? But what that fails to explain is how come these ones, right? What makes these special, right? How come those defy this trend, right? Despite being the lightest set of the species, they have the highest boiling points. So that means there's got to be something else that we need to discuss, right? And that something else happens to be hydrogen bonding. Now, the word is annoying because when you say H bonding, you want to think that it's a bond, right? And it sort of is, right? In terms of classifications, hydrogen bonding is the strongest of our intermolecular forces, and it is sometimes considered a bond, right? For our purposes, though, it is strictly an intermolecular force that happens to be referred to as a bond, okay? Now, you have to commit the definition to memory, okay? It is a hydrogen bonded to an F, O, or N, okay, which is then attracted to the lone pairs on neighboring F, O, or N atoms. Okay, a hydrogen stuck to an F, O, or N, and then is subsequently attracted to the lone pairs on neighboring F, O, or N atoms. Okay, so the simplest way to look at this is that it is just a really, really polar interaction. Okay, where when we talk about ionic compounds, that is just also an extreme case of polarity, right? So polar, in fact, that instead of sharing, they just give away their electrons, okay? Likewise, this is sort of, kind of the same idea, right? Where it is so polar that we give it its own special name, but really it is just an extension of polarity. Where here, if we think about this, right, fluorine is very electronegative, right? Which means that this end is definitely negative, this end is definitely positive. Okay, more so than in another molecule that doesn't include hydrogen bonded to an FO or N. Okay, now if we look over here, hydrogen is then attracted to the lone pairs of a neighboring FO or N, right? Hydrogen is attracted to the lone pair on a neighboring FO or N, which means that for hydrogen bonding to occur, it must meet both of those criteria. Okay, we have to have a hydrogen bonded to an FO or N that can then be attracted to the lone pairs on a neighboring F, O, or N. That whole thing has to be met in order for hydrogen bonding to occur. Now, quick note about hydrogen bonding in water, right? I assume everybody's had the experience where you froze a water bottle and then it got all, misshapen, and if you're unlucky, it actually popped the lid off, okay? Or soda, if you put a soda in the fridge, because they're mostly made of, ding, 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 water, right? So if we look here, this is what solid water looks like. Right? And it's just like if we think back to that picture of the acetonitrile molecules, when they're in a solid, they're always going to arrange in the best possible way to make the most interactions in terms of your IMFs, right? Which means that by default, we end up with these giant holes, which is why as a solid, water actually takes up more space than it does as a liquid. Because as a liquid, these don't always have to be in this right organization, right? It's okay if they spin around each other, right? And sometimes have repulsions, but overall, it's going to be a net attraction, right? Solids not that way, right? They're going to stick themselves in a way where everybody is attracted to its neighboring molecule, which means that, we get an expanded structure, which is why the density is lower, right? If you think about that, right? If it takes up more volume, and density is mass over volume, yes? Fantastic. All right, next up we have our ion dipole forces. We will only discuss ion dipole forces when we talk about solution formation. Only discuss ion dipole forces when we're talking about solution formation, right? Because we're going to have ions from our ionic compound, if it's ionic, okay? So obviously if it weren't an ionic solute, we would not discuss ion dipole forces, okay? So we have our dipole force from the water and our ion here, right? And again, this is sort of what we've been depicting since chapter 4, right? Where the appropriate ends of water will find themselves attracted to the appropriate ion, okay? And again, we will only discuss that in reference to solution formation of an ionic compound. All right. So if we were asked to identify the IMFs present and then select the substance with the highest boiling point, what would we have to do first? Right, we would have to draw it first. So polar or nonpolar? Right, nonpolar. This one, polar or nonpolar? Right. This one? Right. Okay, very good. So we have our polar and nonpolar labels. Okay. Now, what about hydrogen bonding? Well, LDFs. Do they have LDFs? Yes, they all have LDFs. Now, what about hydrogen bonding? Here? No. Here? Yes. I don't know why I did it that way. Whatever. And here? Yes. I'll just stick with whatever I wrote on the last one. Okay, so then in terms of boiling points, right, remembering that IMFs are summative, okay, here it's going to be the lowest boiling point, right? Because all this has is LDFs as a force of attraction, okay? Thank you for listening. Be good, and I will see you soon in the next one where we talk about solution formation. All right, be good. See you soon. Bye.